If you want to understand how a computer works, the best way to do this is to design and simulate your very own CPU. That's a central processing unit, which is the beating heart of a modern computer. In this blog, I'm going to talk through the full design of our 8-bit CPU. We're going to design our own instruction set, design our own assembly language code, write our own assembler, and we're going to simulate the CPU both in the digital design tool called Logisim and also in Excel VBA. There are 9 hours of lectures, and all the designs you see in this blog, which I'm going to talk through today, are fully explained. In a nutshell, if you want to understand how a computer works, then why not design, build and simulate the entire fully functioning 8-bit CPU along with me. Let's watch this 2-minute video which will show you the design philosophy for our 8-bit CPU. I hope by the end of this blog you'll have a better understanding and intuition as to what a computer is and how it works. We will start off with a little bit of philosophy about timescales. Then we'll move on to the basic building blocks of a computer. From now on, we will not use the term computer. We will instead use the term CPU, which stands for Central Processing Unit. If you like, this is the beating heart of a computer, and all our other chips and memory take their lead from this one chip. Now, you might have heard of CPUs such as the Intel Pentium. We then go ahead and we look at registers, a RAM, accumulator and ALU, that's an arithmetic logic unit. We then write our first program in pseudo assembly language. Now, don't worry if you don't understand these terms yet, they'll become apparent as we work through. We then look at the clock and then move on to the control unit and look at machine code, assembly language, an assembler, debugger, simulator, and finally move on to the realization of this CPU in an online tool called Logisim that allows us to build and simulate our entire CPU. It's easy for humans to comprehend timescales such as seconds, minutes, hours, days, months, years, and possibly centuries, as these are directly related to the timescales in which we exist. Centuries may be difficult for some, but for, say, a scholar of history, he or she may have a better feel for what can happen in 1,000 years. But what about larger geological timescales? Tens of thousands of years, hundreds of thousands, 1 million, hundreds of millions. What does the passage of 654,732,433 years mean to you? Now, it doesn't mean a whole lot to me, other than the facts that geologists tell us about shifting continents around the globe. Okay, I hear you shouting now, what have geologists got to do with how a computer works? Well, in this section, I'm going to try to give you a feel for the different timescales a computer lives in, and what that means for us living in a human timescale. So bear with me, I'm setting the scene here that will be very useful for our understanding of the power and usefulness of computers. So now let's go the other way down into the computer timescales. I have an intuitive grasp of fractions of a second. Now, I know that my reaction time is about a quarter of a second, so I might say something like, I can do no more than, say, 4 physical things in 1 second. Now, granted, I can't think of any 4 physical things I can achieve in 1 second, other than, say, jumping in shock to 4 fireworks going off each at a quarter of a second interval. Now, it's not very useful at all. So what does 1/100th of a second feel like? Well, sportsmen and women, timescales up to 1/100th of a second are something that they would well understand. But what about 1,000th of a second, 1/10,000th, 100,000th, or even a millionth of a second? Now, what does 1/654,732,432 seconds mean to you? I mean, again, it doesn't really mean an awful lot to me, but I would suggest that these tiny timescales, they're possibly more comprehensible to us humans than the vast geological timescales. And why is that? Well, because of the invention of computers. Now, it's only in the last 30 years that humans have created machines that work in the tiny timescales of hundredths or even millionths, or now billionths of a second. So how does this make it easier to comprehend these timescales? Well, simply because we can turn these tiny timescales on their heads, quite literally, by asking, how many things can this machine do in a second, a minute, an hour, or a week? This brings these tiny timescales into the realms of human time. We can't do the same with geological timescales. Now, we cannot, or we would simply have to live for billions of years in order to fully comprehend the huge geological timescales. But we can take tiny timescales and we can shift them to human timescales and live out in real time the meaning, if you like, the effect of a small timescale. But we can't squeeze geological time into human time, live out the experience and the meaning or effect or consequences of geological time in a human timescale. Now, we can say it is in the last 30 years that humans have been able to time travel, not backwards or forwards, but into the realms of tiny time, or as I like to call it, computer time. These timescales have become accessible to us, and we can now see the effects of this new realm of time that we now have access to. So before we leave these somewhat philosophical musings, let us put into perspective the power of a modern computer. Let's say that you're a bricklayer and you can lay 1 brick every 5 seconds. Now we have a bricklaying computer, now stay with me here, who can lay 3 billion bricks in a second. So in 5 seconds you have laid 1 in 5 seconds. The computer has laid 3 times 5, which is 15 billion bricks. So 1 square metre brick wall, that is 2 bricks thick, will take approximately 120 bricks. So the computer bricklayer can make a 1 metre high wall 125 million metres or 125,000 kilometres or 77,671 miles long. So in the time it takes you to lay one brick, the computer bricklayer has built a wall 1 metre high 3 times round about the earth. Okay, but a computer doesn't lay bricks, so we know it can do a mind-boggling number of things in a second. So what are these things a computer does, and how can we harness it to accomplish something useful in human time? Let's talk about this through the rest of the blog. What are the bricklaying things that a computer does? To understand this, let us suppose that we want to design and build a theoretical computer machine that adds 2 numbers together. Now, why add 2 numbers? No reason other than it's a good place to start. We first ask the question, how do we add 2 numbers together? And then we say, let us create a machine that mimics this process. Although we replace the word process with a fancy word that means the same, an algorithm. If you like, a mathematical process. We start off with 2 numbers in our head. We don't have a sense of where these are stored in our head. They're just there, but it's just common sense to think that we will need a place to store the numbers in our machine. We call this local storage registers. Why call it local? If you add 2 numbers together, say 5 and another huge number, then you might keep 5 in your head and the other huge number on a separate piece of paper. The 5 in your head would be local storage, and the other large number on the paper could be called remote storage. So registers are just storage locations to hold information that we are looking to work on. By working on, in this case, we mean add. A modern computer might have 8, 16, 32, 64 or even hundreds, depending on the particular architecture of these registers. Now, in our CPU, we're going to have 4, and we're going to call them R1, R2, R3 and R4. Now, we're not interested in how these things are physically built for the moment. We just want to know why we need them and what they're used for. So let us represent them as boxes for now. So you can see the 4 registers in the image opposite. We've got R1, R2, R3 and R4. Now don't worry, we will talk our way through the rest of this image. Now when we do the addition, we're going to have to put the 2 numbers into registers, then do the addition, then put the answer somewhere. So we need to be able to write information into the register and read information out of the register in the same way we juggle numbers about in our heads. To do this, we have 2 inputs to the register. We've got our S and we've got our E. Now S stands for set. This allows us to write information into the register. And the E input stands for enable and lets us read information out of the register. So if you like, the S holds open a gate and lets you enter the register, and the E holds open the same gate and lets you leave the register. So when you come into the register, where are you coming from? And when you leave the register, where are you going to? The answer is in the blue path all the way around the machine. So that's this blue path here. And it's called the bus. So the set allows you to enter into the register from the bus, and the enable allows you to leave the register onto the bus. Now we're going to talk about this section here, which is the RAM. This stands for Random Access Memory. Now this is the remote memory, just like a piece of paper that you would write one of the large numbers on that you're going to add or multiply. This area stores vastly larger amounts of information than the local register. Now, my first computer was a Dragon 32, which I got in the Christmas of 1982, and it had 32 kilobytes, so that's 32,000 bytes of storage. Now, we can now buy external drives the size of your hand with terabytes of storage. Now, we can build up this RAM using the same basic building blocks that we used to build up the registers. Our computer will have 256 bytes of RAM. You see, the RAM also has a set and an enable to control the information in and out of it. So you can see the set and the enable here. All right. Now, as this storage is vast, we need to know our way around it. There's a little block called the memory address register, and you can see that here, MAR, memory address register. Now, we use this to point to a particular memory location in the RAM. So, if we want to put the number 5 in memory location 147, we can first put the number 147 into the RAM. Then when we write the number 5 to memory, it will go to the correct place in this memory address 147. Now let's look at this section here called the ACC, which is accumulator. Now the box just below this ALU, which is the arithmetic logic unit, that is the accumulator. Now it sounds fancy, but this is just another register like R1, R2, R3 and R4. It stores the answer to the arithmetic operation that we've completed in the ALU. We want to be able to control the flow of information around our CPU. We do not want information to just randomly appear on the bus. We can control the flow of information out of the ALU onto the bus through the set and the enable pins on our accumulator. So again, you can see the set and enable pins are controlling the flow of information from the ALU onto the bus. Now let's look at this block here called the ALU. This stands for Arithmetic Logic Unit. Now we need to be able to add two numbers together, and we do this inside the ALU, and the ALU will perform functions such as addition and subtraction and a few other funky things which we'll talk about later. So what we are interested in is how do we shuffle the two numbers around our little machine in the correct order in order to add them together. So what I've done is created something called some pseudocode. So this is like, if you like, a little bit of code which is just a description of what we're going to have to do with this ALU or with the entire CPU in order to add the two numbers together. So we have done this in minute detail, but we'll take our time to just work our way through it. You'll need to do this once in order to get an understanding or an inclination of how this CPU works. So let's say that we've got the number 5 in register R1 and we've got the number 7 in the RAM location 147. So we're going to have 5 in here and we're going to have the number 7 in our RAM location 147 somewhere in the RAM. And we want to bring both of these together out to this point here, and we want to add them up, and we want to take the answer out and we want to take it back and put it back into a memory location here, which is say memory location 148. So these are the steps that we're going to have to work through in order to do this. So first of all, we're going to have to enable R1 with that, is we have to write 5 onto the bus. So we come up here, what we're going to have to do is we're going to have to make the enable go high on R1 because this opens up the gate here and allows whatever is in here onto the bus. So we take our number 5 out of here onto the bus. Now straight after we've taken our 5 out onto the bus, the 5 tries to get into every single point that's connected to the bus. But it will only go into the point which has had a set going high because the set in effect opens up the gate and allows it into another location. So what happens next is the set goes high in this temp register. So it means that value of 5 comes out of here and goes into the temp register. Now in this instance here, we don't need to bother about this section here for the moment. It just passes all the way down and it just sits in here. So now we're going to have the value of 5 sitting in the B port of our ALU. Now the other number we're interested in is the number 7, and it sits in memory location 147 of this RAM. So in order to get access to this, we're going to have to tell the RAM that we're interested in memory location 147. So we're going to have 147 sitting somewhere within these registers. So let's say, for example, we have 147 sitting in register R2. Now it's quite reasonable for you to ask, how did it get there? Well, it got there as part of our program, but we've not talked about our programs so far. Let's just accept that there's a 147 sitting there for the moment. So what we're going to do is we're going to have to enable that 147, that is enable the register R2, that is we're going to have to read the information out of R2 onto the bus. So when we read that 147 out onto the bus, we can then set the memory address register, that is we open up the gate and we let the number 147 flow into this memory address register. So this tells us the RAM, tells the RAM that we're interested in that memory location. We can then enable the RAM, that is we can read the information from memory location 147 onto the bus. So the number 7 gets read out of memory location 147 out through this output and it goes on to the bus. And it tries to get into every other part here of the CPU, but it won't get into any of these registers because all the enables, all the sets have gone low, so it won't allow them to write anything into any of these areas. But it can come up and it can come down, and you can see it can actually come in here because there isn't any set or enable here in this line, so everything can just come in and sit at this point. So now we're going to have the number 5 sitting here and the number 7 sitting here. Now these 3 lines here control the operations of the ALU. So let's say, for example, they're sitting at 000, and in this instance the 000 would be telling the ALU to add the 2 numbers together. So this addition would take place and we would have a number 12 sitting here. Now we could then make the set go high, which will allow that number 12 to flow down through into the accumulator. Now that number 12 is going to be stored in memory location 148 in the RAM, but again we're going to have to tell the memory address register that that's where we want to put it. So let's say we've got the number 148 sitting in register R3. We can enable R3, which will put the 148 onto this bus, and then we can set the memory address register, which puts the number 48 into this memory address register. We can then enable the accumulator, that is we'll allow the number 12 to come out of the accumulator onto the bus. And when we do that, we can then come down and we can pulse the set on the RAM, that is we can write the number 12 into the memory address, which is pointed to by this memory address register. So we'll read the number 12 into the RAM. So that's how we add the 2 numbers together, our numbers sitting in register R1 and also sitting in the memory. And finally, the addition of those 2 numbers will be put into the next memory location. So you can see how long and involved and Rather tedious it is, but it's worthwhile for you just to read through that once more yourself and be sure of everything that's happening in order to add these two numbers together. Now, the thing that always confused me was the exact interface between the software and the hardware. What is the software and what is the hardware? And where do they meet? Where is that interface? Well, from what we've seen there with that example, the software is the set of instructions that controls all the sets and enable pins. So let's have a look up and we'll see what I mean by that. You can see here that we've got set and enable pins in every single one of these blocks, although some of the blocks have only got sets and don't have enables. But the set and enable pins control the flow of information round about the CPU. So the software is the code which tells us what sets and enables to turn on and off at what time. So let's just have a wee repeat of this. The software is the set of instructions that controls the set and enable pins that control the information flow around the CPU. And also you can see in that instance it chooses, for example, the ALU function. Now the hardware is the actual physical implementation of the blocks. So the best thing to do, read over that a few times and think about it, because it's important that you get that, because it's quite fundamental. So if there's only one thing that you're going to take away from this entire blog, and you're going to remember in several years' time, is that hardware is the physical implementation of our switches, and the software is the instructions telling the machine in which order to switch. So let's go ahead and see how we're going to control the switching using a clock. We want to control the flow of information around the CPU. We do this by making sure that everyone synchronises their watches, just like in the old movies. We want to make sure that every part of the CPU works from a central watch, or more commonly known as a clock. So let's talk through below and we'll see how information passes from one register to another register using a clock. So let's look at this clock diagram here. We're going to start off with this master clock here, and you can see it's ticking away. And we're going to have this other clock here, which is a delayed clock. So you can see it's the same clock pulse here, but it's just been delayed slightly. Now we can use these two clocks in order to create another couple of clocks, which we're going to call our clock E, which is enable, and clock S, which is a set clock. Now it doesn't matter how we've generated these two clocks down here from these two. We'll get into that in more detail in the full course. All we have to know is that we're going to have this enable clock here, and we're going to have a set clock. And the thing about the enable clock is the enable clock completely encompasses the set clock. By that I mean that whenever this set clock goes high and then low, it does it within one time frame here of the enable clock. So let's draw just one section of this up here. So let's take this little section here and we'll redraw it up here. So we're going to have an enable clock here which completely encompasses the set clock. So let's say we want to pass information from this register here into this register here. So let's say the number 5 is on this register. In order to pass the information from this register into here, first of all we have to make the enable go high. So the enable goes high in this register. That is, we read the number 5 onto the bus. So once we've read the number 5 onto the bus, we want to place that information into this register here. Now we do that by making the set go high in this register here. So we read the number 5 into this register, and that's this high point here. Now, after it's been read in, we then make this set go low. So once the set goes low, that number 5 is captured or held within that register. Then finally what we can do is we can make the enable go low in this register here. So whenever the enable has now gone low, it means that this is the final part of the process. The information number 5 has come out of here, moved along, and it's gone into this bus here, into this register here. So that's how we pass information around about the chip or the CPU in an orderly fashion by using a set and an enable clock. Now let's move on to the really interesting part of the CPU design, and that's the control unit. So if the CPU is the beating heart of the computer, then the control unit is the beating heart of the CPU. So we've said that in order to allow this CPU to do useful things like adding two numbers together, we have to control the flow of information round about the CPU, and we do that by changing the set and enable values in the registers, in the temp register, in the RAM and the memory address register, the accumulator, and the ALU. Now, the unit that controls all of this flow of information is called the control unit, and this is what we're going to talk about over the rest of the blog. So we've seen that the control unit lies at the heart of our CPU. All the sets and enables come from the control unit. In this little CPU we've designed there are 21 separate lines connecting to it. When we write a program, we control all these lines and we make them go high, that is a 1, or make them go low, that is a 0, and we make them do it in a particular order or sequence. Now this is what we call our program. So our program is simply the sequence of zeros and ones which control these sets and enables. So in the second section of this blog, we're going to talk through the control unit. We're going to see the initial design, and we'll work through a far more complex design, and we'll build up our ALU instruction set via the control unit, and we'll build up our assembler in Excel VBA, and we'll work through a few programs, for example a division algorithm, subtraction, and a program that works out the Fibonacci numbers using our own assembly language. And we'll work through the debugger as well, and you'll see the CPU actually simulated within Excel VBA. And we'll talk through the top level of our design and each of the blocks. So this is the top level design, and this is the ALU, and we've got our RAM, and we'll have the control unit. And as you see, the control unit looks quite complicated, but we will talk through in tiny small chunks, and we'll divide and we'll conquer and we will understand it. And finally we'll look at our top level and we'll work through an actual program. So we'll get to that in the next video. Thank you for listening, and goodbye.